Hi guys, this is Emily from Flutter by Farm. I had promised a few weeks ago that I was going to do a little bit of an informational on the genetics and heredity of polled and blue-eyed goats. Taken me a couple weeks to get to it, and I apologize, but here I am today. All right, so I'm a registered nurse. I was really fortunate to be able to study at a university level a semester of genetics and heredity, and then also a semester of biochemistry. I don't want you to think that that makes me an expert in this, because this is the kind of material that you get a PhD in and you spend your entire career doing research. I am by no means an expert. I have a basic understanding. I think that understanding has served me well in my herd through the years, and has kind of given me a greater of understanding even in much more complex scenarios. Okay, so I want to start with DNA is made up of proteins and protein bonds, and because of those bonds and the way they are formed, it looks like a spiral staircase. For the purposes in this video, though, I have kind of stretched out and straightened it out just to make it a little bit more simple to see. Okay, so here we have a piece of DNA that I have stretched out and made to look more like a ladder. Okay, it's made of proteins and protein bonds, and this is a gene. Okay, it's got two sides, and there's an allele on each side. This is an allele. Okay, it's just one, and then the two together across from each other that have a relationship make up a gene. Okay, now if we were to take this invisible line and just cut down through here, cut this ladder in half, you would have half of this side possibly coming from the sire. So this is going to come from the sperm. This side is going to come from the dam, the egg. Okay, when you put the two sides together, you get a gene. Okay, the reason why this is important, because it's important to realize that you're getting half of this from the dam and half of this from the sire. Okay, so heredity is the inheritance of genetic material. Some traits are controlled by a single gene. Others are controlled by multiple genes. Blue eyes and polled genetics are simple because they're only controlled by a simple gene. When you get into top lines, udders, leg placement, other things, it can be really complicated because you have numbers of genes that are working together to kind of determine that heredity and what that offspring is going to look like. If you can kind of understand this, you will have at least a basic understanding of how these things work, or a better understanding. Again, this is really complex. Honestly, if I did a lot of research, I might grasp this, but I wouldn't promise you that. Okay? And this is going to be nerd stuff at a level that most of us don't even know where to find it. It would probably be more related to either cattle or horses, because there's just not a lot of money put into goat research. Okay, just gonna be honest with you there. It's sad, it's terrible. You can have dominant alleles. That means if they are present, they will automatically show themselves. If you have a recessive allele, it's only going to present itself, to show itself, to be the phenotype, what you see if there's two copies. Because if there's not two copies, then you've got a dominant and recessive together, and this one is always going to be the one that kind of steps out with his chest out and says, see me, okay? So if two recessive alleles are present, they will show themselves, but if there's a dominant, it's not going to happen. They're hiding, okay? Now, phenotype is important because you can have a couple of different scenarios that result in the way of an animal that looks the same, okay? And so what is expressed is what we're seeing, and that's kind of what we prioritize as breeders, okay? But you can have a homozygous situation, either dominant or recessive, where you have two of the same alleles, the homo root meaning same. You can have a heterozygous situation, which means it has two different alleles, the root hetero being different, okay? So dominants are generally written in capital letters, and recessive written in lowercase letters. So homozygous would be like a double big H or a double small h. They are the same. Going back up here, okay? Heterozygous means you've got two different ones. Going back here, that root, okay? So you've got a dominant and a recessive. All right, now this is a Punnett square. This is like, you might have even done a little bit this in like high school biology if you really think back hard, okay? Okay, so what I've got here is I have an example of polled genetics. And the way this conversation kind of came about on one of the boards a couple weeks ago was we were talking about the generally accepted belief that breeding two polled goats will result in a higher probability of sterilized offspring. Okay, there was a study done. The sample size was very low, and don't quote me on what it was, but I mean, we're not talking thousands of goats. We're talking about very small numbers, maybe dozens. And when you only have dozens, there's not really enough repetition there to say that it is scientific fact, okay? But in general, we as breeders kind of accept it as fact. So if you have a polled goat, it's probably going to be a situation like this where he has or she has a dominant and then a recessive allele, because in order to get a double dominant, you would have to breed two polled goats, okay? And we just don't do it. That being said, I have a herd sire out my barn that is polled, and I know for a fact, just looking at his genetic history, that he is going to be a heterozygous polled goat. And then I don't have any polled does, so all of my does fall under the homozygous polled, or horned, horned. So this is an example that I could very easily see in my barn. And the way this works is once you set it up, so it kind of reflects what you're doing in your barn, you can start pulling these down, okay? So we're gonna take this polled allele and we're gonna pull it down, okay? Now, over here, he also has a recessive gene. So on this side, we're gonna pull down his recessive horned alleles. Now, my does here, they have all horned genetics, the recessive ones. We're gonna fill those in. This one comes across here, this one's gonna come across here. Okay, so when we look at this, we see that we have, resulting from this breeding, two polled goats and two horned goats. Now, do not trick yourself into thinking that if you have this breeding and you have 4 kids, you are going to have 2 polled goats and 2 horned goats. Because this is actually probability-wise, mathematically speaking, chances per goat. So if each one of these is 25% to make 100%, you've got a 50% chance of each offspring being polled and 50% chance of each offspring being horned. But if it's not a good year, or all the horned sperm win that year, you could easily end up with 100% horned goats, even though there was a 50% chance of each one of them being polled, okay? So to kind of recap, out of this breeding, we've got the result of the possibility of either heterozygous polled or homozygous horned animals, and it's a 50-50 split between the two. Okay, so now we're going to kind of move on to, there's not as many possibilities with polled because generally we don't do polled to polled, okay? And clearly if you were to fill in, if you were to switch this column to being a horned goat, well, guess what? Then you're going to bring this down to, with the little p's, the recessive genes, you've got a horned to horned breeding, which is going to result in a horned breeding, a horned kid 100% of the time. So, but blue eyes is where it gets a little bit fun, okay? Now, blue eyes are dominant, which surprises some people, okay? So we've put that in blue, and it's with a capital letter because it's dominant, and that's just the generally accepted way that we do things when we're talking about heredity. Brown eyes are recessive, so I put that, just left that in black. One side is going to represent the sire and one side the dam. It doesn't matter which, okay? In this scenario, I have a blue-eyed sire. He had a brown-eyed mom, though, so I know he's only heterozygous. And then I've got a brown-eyed dam. So this sire is going to take his blue allele and bring it down this column, and his brown allele and bring it down this column. Well, she only has one thing to give. She's got 2 copies of brown, so hers are going to be, her side across are going to be brown all the time, okay? So the result of this breeding would be a 50% chance of blue-eyed, but they're all going to be heterozygous. and a 50% chance of brown. Now remember, 50-50 is per goat, not per breeding. So you could still end up with 100% blue-eyed goats, and you could end up with 100% brown-eyed goats, and that's going to be their phenotype, what they actually express. Okay? Now, this is where it gets a little more fun. Here we have a situation where we are going to breed two blue-eyed animals. They are both heterozygous blue. The sire, he's going to bring down his dominant blue gene. And then over here, he's going to bring down his homozygous recessive brown-eyed gene. Now over here, the dam is going to bring across her dominant gene. And then down here, she's going to bring across her recessive gene. So the results are, and this is kind of funny, we haven't seen this yet. This is a homozygous blue-eyed goat. Now, there's a 50% chance of heterozygous blue, which is just like mom and dad, and then a 25% chance of having a brown-eyed kid, okay? Now, as far as phenotype, as far as what you're going to see a 75% chance of blue-eyed babies. But what happens if you end up with a homozygous? Now, let's be honest about something. In goats, how do we know if an animal is homozygous blue-eyed? Well, it's probably going to take years to figure out that he or she is absolutely never had a brown-eyed baby. There's not really genetic tests we do for that. We know in certain breedings it's possible, it could happen, but it's not really proven until years have gone past, okay? So, now, let's say, what happens if we take this kid next year and breed this kid? Oh, well, let's take a look. So, if we have a homozygous blue-eyed goat and we breed with a heterozygous blue-eyed goat, what we get is dam's coming across here with her dominance, sire's coming down here with his dominance, and I got ahead of myself, so I didn't fill in these. So now we have a 50% chance of the homozygous blue eyes and a 50% chance of the heterozygous blue eyes. Again, going back to, we can't really prove they're homozygous until a couple years have gone by and they've never had a brown-eyed kid. If you really wanted to play around, you could breed them for a couple. I mean, these are all scenarios, though, that most people who are going to watch a video like this are never going to encounter, because that's just not what we're breeding for. We're breeding for milk production. We're breeding for conformation. The blue eyes is just the icing on the cake. But this is what it starts to look like when you start to get into homozygous blue eyes. And it's kind of cool. But remember, when you're looking at udders, attachments, anything like that, there's multiple genes in play. So it's a little bit more complicated than just, let's throw together a Punnett square and work it out. But if you understand that there are dominant and recessive genes, then you're more able to kind of weather the disappointment when a animal throws a trait that you're not super excited about, and know that there's still a possibility. Don't throw the baby out with the bathwater, because they very well could have just thrown a recessive gene that year, and maybe next year is better, or maybe they've had a couple of years where they've thrown great kids, and then the next one comes out and you're like, what happened? Well, it might have been that sneaky recessive gene, and that's also kind of why some lines just don't mix. You ever notice that maybe you've got a sire or a dam that they always throw beautiful babies, but if you try to put them with that particular mate, it's always a disaster. Well, maybe they're both carrying the same recessive gene, and that's why they don't mix together. So if you just don't mix them together, or if you can get a little bit lucky and not accidentally put them with another animal that has the same recessive gene, then it's okay, because you never see that gene, okay? So I think these are all things to kind of consider when you're looking at your herd and when you're trying to plan for herd improvements, hoping for herd improvements. And I hope you can add it to your strategy. If you have any questions, feel free to contact me. I'd love to help if there's any way possible. But again, remember, I am not the genetics guru. I am just a nerd. Thank you very much and have a great day. Hope you have a Merry Christmas.